Yeah, thank you. Got it. Okay, thank you very much. Yeah, and thanks for the organizers for inviting me. It's a real honor to be speaking here. I actually thought I'd start with a little anecdote, which is that, during the talk, topological Hochschild homology will come up, as you might imagine from the title. And the very first place I learned a definition for topological Hochschild homology was actually through the eCHT program, was actually during a mini course Akil Matthew gave. So, yeah, it's fantastic to be back here now on the other side of things. Okay, so, right, so I'm going to talk about, well, a prismatic description of K-theory of certain rings. And so to get started, let me just talk a little bit about, what objects are we studying? So, okay, and right, so the first thing to answer is, well, what is algebraic K-theory? What is this K-theory object? And I mean, unfortunately, that's a whole pack of worms. I won't have time to go into exactly what it is, but let me just sort of give you the idea. So K-theory, what is it? Well, it's a functor from something to something else. And the source and target can both be extremely general. It more or less depends on, what you're willing to put up with, really. But the rough idea is it takes in some algebraic data, thought of in sort of the loosest possible terms, and it'll spit out a spectrum. And a large goal of algebraic K-theory, the study of algebraic K-theory, is to compute the homotopy groups of this spectrum. Okay, and then for us, we'll just think about the input as being commutative, just discrete rings, commutative algebras. Okay, and roughly what this is doing is it's an invariant built out of sort of the perfect R modules. So I'm describing K of R here, where R is some ring. Okay, and it's universal in a certain sense. Okay. So it contains a lot of very, very deep information about the category R and specifically about perfect R modules, or if you prefer, since we're working with discrete rings, you can think of these as sort of projective finitely generated R modules. And the other thing I want to mention about K-theory is that it's sort of famously very hard to compute the homotopy groups. So very hard to compute the homotopy groups. Okay. So there are a couple of ways people have tried to study algebraic K-theory. One of the most successful ways is by comparing it to a much more computationally accessible theory, which is Hochschild homology. So K-theory, just by one of the definitions, it'll admit a natural transformation to Hochschild homology, over the integers if you prefer. And in fact, this map, this natural transformation, factors through a topological lift of Hochschild homology, which we call topological Hochschild homology. Okay, and this will have a map this way, and we have a map this way. And it turns out that this map is a very, very good comparison, depending on how much structure you consider THH as having. So, okay, so what is THH? So throwing quite a lot of definitions at you, but oh.
Sorry, so your K-theory is non-connective, right?
No, I'm just thinking about it as connective. I mean, it'll turn out not to matter for truncate polynomial algebras. No, that's not, well, it depends on, I'm working with connective K-theory. Let me just say that. Okay. Yeah. It'll turn out not to matter for the type of question I'm going to consider, and I'll mention that in a minute. Okay. So what is THH? What is topological Hochschild homology? Well, topological Hochschild homology will take in, again, the input can vary depending on how much you're willing to put up with. But let me just say that it'll take in infinity algebras. And really, I mean, infinity ring spectra here. And its output will be a spectrum with an S1 action, and I'm going to use T for the one torus for S1, just to really emphasize that we're thinking of it as a group. And it'll have some additional structure, plus epsilon. Okay, and I'll explain what these are in a minute. Okay, and so what is this object? Well, if you have a ring R, THH of R, one definition, or equivalence, depending on how you want to think about it, is that this thing is R tensored with the circle, and you take the tensor in the category of infinity ring spectra. Okay, so, you know, if you haven't seen this before, what does this mean? Well, one way to think about this is that you can build up spaces just using points and homotopy co-limits. And what this tensor operation is doing is saying, take some representation of your space as co-limits of points and replace the points with R and replace the co-limits of spaces with the co-limits of ring spectra. So here's one model for the circle. You can take two disjoint base points, or two disjoint points. You can map them both to a point, and you can take the push out, and that'll give you a copy of S1. Okay, so this formula is telling you that then if you replace points with R and co-limits and spaces with co-limits in infinity ring spectra, okay, so the co-product in the infinity ring spectra is the smash product, or the tensor product over the sphere. And then the push out in E infinity rings is going to be the relative tensor product. That this will be a formula for THH. Okay, and if you're familiar with Shukla homology, which in many cases is the same thing as Hochschild homology, well, there you go, there's a comparison. And if you only prefer the sort of usual sort of chain complex model of Hochschild homology, well, here's another way to think about THH. You can think of the circle as having one non-degenerate zero simplex and one non-degenerate one simplex. Okay, so you have one non-degenerate zero simplex, one non-degenerate one simplex, and then you have a degenerate one simplex. Okay, and then you start studying the combinatorics of like how many degeneracies you need to form this simplicial set, and you see that in degree n, you'll need n plus one degenerate doodads, and then so on and so forth. The geometric realization of this thing will be S1. And so to get THH, you can do R tensor R tensor with itself 3 times, so on and so forth. And this geometric realization will be THH. Okay. And you can check, that these boundary maps are indeed the sort of usual boundary maps in the Hochschild homology complex. And again, by tensor, I mean tensor over the sphere spectrum. Okay. Great. And so that's what THH is. And manifestly, right, if we go back up to the definition, it's going to have an S1 action just by, well, we're tensoring with S1. So just act on that copy of S1, that'll give you an S1 action. And it turns out that this natural transformation, K theory of whatever to THH of whatever, is equivariant, where we consider the trivial S1 action on K theory. And so we actually get a factorization through the homotopy fixed points. Okay. So great. So this turns out to be, this map turns out to be a much closer comparison, but still not quite strong enough to get the computations we want in K theory. Okay, and so I said that THH lands in spectra with an S1 action plus epsilon. Well, what's that epsilon? Well, that epsilon are maps of the following form. So you have THH of R. They come equipped with equivariant, S1 equivariant maps, which we call Frobenius maps, BP, to THH of R, Tate CP. And this is for all primes P. For all P and P, here P is the set of primes. Okay. If you're more familiar with the genuine side of the story, what is this map? Well, we know that THH of R is equivalent to its genuine CP fixed points, equivariantly. And then there's always a natural map from the, sorry, not the genuine, the geometric. And there's always a map from the geometric fixed points to the Tate construction. And that's one way to think about what these maps are. Why are they called Frobenius maps? Well, THH always admits a non-equivariant map from Rm, and THH of R Tate CP will always map to R Tate CP. And so you can ask what this composition is. And well, it's a map built out of a bunch of power operations. But maybe let me just say that this map on pi 0, what is this map? Well, this is a map from R to R mod P. And what is this map? Well, first it's modding out by P. So mod P. And then it's the Pth power map. So it's a composition of these two maps. So this is one of several reasons why we call it the Frobenius map. Okay. And K theory, well, sort of respect this structure in a certain way as well. And so that leads us to a further refinement. And so you can either take this as a definition or as a theorem. And this is due to Nicholas and Schultz. And again, I'm really only, at the end of the day, going to be thinking about discrete rings. So what I'm going to say is not going to be 100% true for all rings. You need some bounded below hypotheses, but let me just sweep that under the rug for the moment. we get a new invariant called TC, topological cyclic homology of R. And this is either defined as or equivalent to, depending on how you want to think about this, the equalizer of the following two maps. So you have TC minus, which is the homotopy fixed points. And then you have the products over all primes of TP of R, P completed. Okay, and what is this? So first of all, TP of R is the take construction on THH. And whenever I write coefficients in DP, what I mean is, so TP of R ZP, this will just be by definition TP of R p-adically completed. Okay, so that's what I mean by that. And so the top map is the product of all the canonical maps. You always have a map from the homotopy fixed points to the take construction. So that's the canonical map. And the bottom map is the product of all these Frobenius maps. Okay. Right. And so I started this talk by talking about K-theory and took a sharp turn into this Hochschild homology TC world. And there's, you know, as you might imagine, there's a reason I'm bringing them all up in the same section, in the same talk. And let me just write the theorem. So the first thing to say is it turns out that the map from K-theory to TC minus factors through TC. And in fact, this map is really an astonishingly good comparison map. So let from A to B. Oh, let me first say that this is due to Dundas, Goodwillie, and McCarthy. So let F from A to B be a map of, well, at the end of the day, we're only going to care about discrete rings. So let me just state this theorem for rings. It's true much more generally, but let me not worry about this. Of rings such that the kernel of F is nilpotent. Okay. Then you can look at the induced map from K-theory of A to K-theory of B. You can look at the induced map from TC of A to TC of B.
You want the map to be surjective.
Thank you. I 100% do. Thank you. And you can consider the factorization of this map to Hochschild homology. This is called the Dennis trace. And okay, this square is pullback. In other words, if you look at the vertical fibers, which I'll write as K of A comma B, or TC, this will be an equivalence. So relative K theory and relative TC are the same for no-cone extensions. And so if you already know, for whatever reason, K theory of B of the base ring, then to figure out what K theory of A is, it's enough to, you know, up to an extension issue, only consider TC of these rings, which tends to be much, much more computable. Right. So this is a fantastic theorem and is the basis of pretty much every single paper I've ever written, including this one. Okay.
May I comment that the Dennis trace used to mean the construction given by Keith Dennis, which was the map to Hochschild homology.
Right.
And then that was improved to a map to topological Hochschild homology by, Goodwillie, Walthausen, and Bergstedt. And then the definition of topological cyclic homology was traditionally by Bergstedt, Chang, and Madsen. So, I mean, there was some work here in the 80s and 90s and 2000s, which, yeah, anyway.
Yeah, I appreciate that. Thank you. Yes. And in fact, I'm going to mention some previous work in a minute, particularly work done by Soleil and Staffeld, and that was done using using this map to HH. So we already had sort of some ideas in the air about such refinements of this Dennis trace being extremely good at computing K-theory, and rationally, we got a lot of computations done before sort of this THHTC definitions were discovered. Yeah, thank you very much. Okay, great. And so, you look at this, you want to understand K-theory, this gives you a tool for computing it and understanding it. And so a natural first step to try is, well, what's the simplest nilpotent extension of a ring? Well, to any ring R, you can take just the truncated polynomial ring R join X mod X to the E for some E. Positive. Okay. And so that's a natural question to ask. Okay, well, what does this theorem tell us in the sort of simplest nilpotent extension case? And yeah, so a lot of people have thought about this. And I don't have time to list everyone. So I'm leaving out, unfortunately, I'm going to have to leave out some really, really great work on this problem, but let me just mention some previous work. So section 2, previous. I'll say some to really emphasize some previous work. And these are the works that are most closely related to what I've done. Okay, so as I mentioned, this was thought about by Soleil and Staffeld in the case when E was 2. And Staffeld when E was greater than or equal to 2. I'm not going to say exactly what they did. They proved things for more general basis than what I'm going to write here, but let me just write one important consequence of what they did. So they showed using some of these technicians that for all integers greater than or equal to 1, the rank of these groups, of the even K groups of Z join X mod X to the E relative to Z, that these were 0. And in fact, we know that for other reasons that these groups are finitely generated. So in fact, the even K groups over the integers of these truncated polynomial algebras are finite. And they also showed that the odd K groups have rank E minus 1. Okay. Great. And so, this is not a complete computation. In fact, to this day, we still don't know the group structure on these even K groups. We do know the group structure on the odd K groups, and I'll say that in a minute. But yeah. So this was done in the 70s and 80s, I believe. Okay. And then a full computation was done by Husholt and Madsen. And this definitely used the TC approach. It was a different definition of TC, but it was an equivalent sort of construction. And so what is this? So let little k be a perfect FP algebra. And by perfect, I just mean that the Frobenius map, the x goes to x to the p map, is an isomorphism. Then they actually computed a very concrete representation of these groups. Then for all r greater than or equal to 1, we have that the relative k groups to the relative odd k groups of k adjoint x mod x to the e relative to k. These are the big bit vectors of length re on k modulo the image of the eth Rishibam. And the even group Spanish. Okay, so very concrete, full computation. And I should mention also that that these relative K groups are products of Eilenberg-MacLean spectra. So this completely determines the spectrum as well. And then sort of next thing I wanted to mention on previous work is that actually this theorem by Soleil and Staffeld was not the end of the story for studying these K groups for the integers. So theorem. This was due to Engeltveit, Gerhard, and Husholt. And they actually computed the group structure on the odd relative K groups of Z and computed the order, the cardinality of the even K groups. So for all r greater than or equal to 1, we have that the even K groups of Z adjoint x mod x to the e del x. Oh, sorry, but Z. These groups have order e times r factorial times r factorial to the e minus second power. And the odd K groups are in fact free of the given group. Okay. And this builds on previous work of Husholt, which this builds on previous work that I haven't been able to mention because of time issues. Okay. So these were some of the highlights that happened before this new definition by Nicholas and Schulze for TC came out, and before Baumor and Schulze introduced the quasi-symptomic site and the techniques I'm going to talk about in a minute. And so after these sort of recent advances, some people have been going back to the truncate polynomials and reproving some previously known results. So I'll say that Martin Spears reproved this Household-Madsen result. Using the Nicholas-Schulze approach, which I'm going to abbreviate as NS. And I mean, it was almost completely a purely algebraic computation. There was very little homotopy theory needed. And then I should also mention that recently Matthew has also revisited this Household-Madsen computation. For E equals 2, using the Bott, Morrow, and Schulze work. Okay. And then Salima did the E greater than or equal to 2 version of Matthew's work. Okay. And you know, these last two, really it's a pure algebraic computation. Sort of because of the work of Bott and Schulze, they were able to sort of rephrase this computation, these questions of these computations, into purely a question about the Durand bit forms and the Hodge filtration on them. Okay. And so what I have been thinking about, what this talk at the end of the day is about is, well, what does BMS, Bott and Schulze have to say about, for example, characteristic zero rings, or more generally, right? All Spears, Matthew, and Salima were all about perfect FP algebras. Can we get some information more generally? Okay. The answer is yes, but to be able to say, you know, what the result is, I'll need to introduce some of the objects from Bott and Schulze. Okay. So section 3. And I'll say before I jump into this that I'm going to give topological constructions of the sort of main sheaves. And from this perspective, it's not super clear that these things are very computable. But for a lot of this sheet, for all of the sheets I'm going to write down, we have purely algebraic ways of studying them, either using sort of this relative prismatic cohomology of Bott and Schulze, or, you know, if you want to work with stacks, there's a stacky approach now being developed by Drenfeld and by Bott and Lurie. And this has led to quite a few computations of these sheaves. So, these, I don't want to give the wrong impression. These are very much computable things in a lot of cases. Okay. So, right. So first of all, quasi-symptomic sheaves. To talk about sheaves, you need a site. What site are we working on? Well, here's a definition due to Bott, and Schulze, which I'm going to abbreviate as BMS from here on out. So a ring R is quasi-symptomic if it satisfies 3 conditions. The first is that R is P complete. So I've switched to working one prime at a time. This is fairly harmless, but it'll just be helpful to only be working with one prime at a time. The second point is that R has bounded P infinity torsion. And the third point is that the cotangent complex of R over ZP has P complete Tor amplitude in -1 to 0. Okay, and so, that's a lot of, what does this actually mean? Well, these first two conditions are saying that R is P complete, so we're only working one prime at a time, and derived P complete. So it's a technical condition so that we don't have to worry about the difference between P complete and derived P complete. If R is the P completion of an Noetherian ring, for example, you don't need to worry about this bounded P infinity torsion stuff. But it's a helpful condition to have around, just so that we don't have to worry about the difference of these two ideas.
So you are using cohomological degree, convention.
Yes, thank you. Yes, yeah. So this cotangent complex, when I say P complete Tor amplitude, this is cohomological degrees. So if you want to work homological, it would be 0. Thank you. Yeah. And then this third condition is saying that we're allowing our rings to be R can be singular, just not too singular. Right. So if R, for example, is the P completion of a regular ring, well, this condition will be satisfied. The P complete part of this definition says we only really care about what's happening mod P, derived mod P, but let me ignore that. And essentially, the reason we allow it to be a little singular is that we want to be able to add in a bunch of P power roots of unity. Okay. So these are the objects. We can form them into a category, which we call QSIM. And there is a Grothendieck topology on this category where the covers mimic the definition of quasi-symptotic. So a map F from A to B is a quasi-symptotic cover if, well, first of all, B is a P completely faithfully flat A module. So on SPOOF, we want B to actually cover A topologically. And the second condition is that the cotangent complex B over A has P complete Tor amplitude. And -1 square. Okay, and it's a theorem of Baumor and Schulte that these notions of covers do form a site, that everything is copacetic. And there is an extremely nice basis for this topology. So sitting inside of quasi-symptotic rings, there is a subcategory of quasi-regular semi-perfectoid rings. And for time consideration, the only thing I'm going to say about this is that these form an I-spaces. And that's one of the main results of the paper of Baumor and Schulze is a computation of THH, TC minus, and TP of quasi-regular semi-perfectoid rings. So we know what those invariants look like on QRSP rings, quasi-regular semi-perfectoid rings. And since they form a basis, to define a quasi-symptomic sheaf, it's good enough to define a sheaf on quasi-regular semi-perfectoid rings. And so what are some examples? These examples are from Baumor and Schulze. Well, you could look at pi 0 of TC minus P completed. It turns out that this is a sheaf of filtered rings. So maybe I'll say filter P complete rings. The filtration is just coming from the fact that this is pi 0 of the homotopy fixed points of something, and the homotopy fixed points are naturally filtered, right? The filtration is given by the homotopy fixed point spectral sequence. This is the sheaf on quasi-regular semi-perfectoid rings. And so we get a sheaf on all quasi-symptomic rings. It will be a filtered sheaf of rings. So I'm going to denote the filtration by N star. And then we have O prism hat. Okay, so this will be a sheaf. Another example of a sheaf is you can look at pi 0 of THH, CP, Tate CP. Okay. This will be a sheaf on QRSP rings. And so we get out a sheaf, which is called O bar hat. Okay. And we have a map from, well, I'll just say O bar hat to this sheaf. And you can look at the fiber. The fiber, it'll turn out will be a line bundle over O prism hat. And this line bundle is called I, the Hodge-Tate divisor. And then the final thing I need to say is that you can also look at TP2, the second homotopy group of TP, CP. And it turns out that this will also be a sheaf on QRSP rings. And the sheaf on quasi-symptomic rings we get out will be denoted like this and will be called the Breuil kiss and twist. And it will be a line bundle over O prism. Okay. And so the statement, so, okay, getting to my main theorem in the last minute. Sorry about that. So main theorem is that in many cases, you can actually write down the K groups of the relative truncated polynomial algebras in terms of the sheaves I just listed, and that these sheaves are very computable. So here's the theorem. Let S be either a smooth curve or over a perfectoid ring, a perfectoid ring, or a complete mixed characteristic DVR with perfect residue field. Such as Z or ZP, because I'm working one prime atom. Then the odd K groups I can't get the K0 or K1, but for all higher K groups, the odd K groups, and we're working one time at a time, so let's just P-complete this. This will be given by the product over positive integers, which are co-prime to P and to E of the zeroth cohomology of S with coefficients in the following sheet. So you take R minus T minus 1 of O prism, and you mod out by greater than or equal to R minus T of O prism tensored with I sub S. And then you take this and you break kiss and twist by R minus 1 minus T over P for that. Okay. And maybe since I have -2 minutes, let me just say times similar terms for the case when E divides U, and then the even K groups are H1 of these sheets. And again, I want to emphasize that these are computable sheets. But yeah, in the interest of time, let me not go into any more of that. The upshot is that we have a description in terms of sheet cohomology for sheets that we can use stacky approaches to. Okay, this time for real, I'm done. Thank you for listening.